Let's look at an example of generating data from a discrete HMM to make it perhaps a bit more concrete. So here's an example of a dishonest casino. And again, this is an example of a discrete HMM. Imagine that we have two dice. One of them is fair and one of them is unfair. What that means is that the fair dice has 6 sides and the probability of any individual side is 1/6. Unfair dice has also 6 sides, but we have different probabilities of which side it will show up when we roll it. Then at each roll, we have a sequence of rolls. We're either going to keep the current dice that we're rolling, or we're going to switch to the other dice, but we're not going to get to see which dice is used. We just get to see the roll. But underneath the table, perhaps, is the choices being made of which dice to pick next, given the dice that was used previously. And all we get to observe is the sequence of the rolls, the numbers that came up. So in this case, we have the 3 parameters for the HMM we need to define. We have a transition matrix. And so let's think of the transition matrix like this. So the first state, we're going to call the first state the fair dice, the second state the unfair dice. And so the probability of using the fair die or the fair dice next in the next roll, given that I use it in the current roll, is equal to 0.95, and the probability of switching to the unfair dice, given that I use the fair dice in the most recent roll, is 0.05. So that's the probability of switching from a fair to an unfair dice. The probability of switching from a unfair to the fair dice is 0.1, and the probability of staying with the unfair dice is 0.9. So this is how we choose the sequence of dice that we're going to use in the rolls. Given that we're at the fair dice, we use the fair dice, the probability is 1/6 of the 6 different observations. So a dice has 6 sides. I see a number, I observe a number between 1 and 6, and so my matrix B has 6 columns. And my distribution on those 6 different numbers I get to observe, given that I use the fair dice, which is the first state, is 1/6. And then if I use the unfair dice with probability 1/2, I have a 6 roll up, and then with the remaining probabilities, I have anything else. And then I have to also pick the first dice that's used, and I'll just say that it's a even probability on either. So this is an example that we'll return to in a later slide of how you would generate data from an HMM. But all we get to observe are the results of the rolls. That's the observed sequence. But the hidden process, the hidden state transition, is picking between one of the 2 dice. We've defined the generative process for the HMM. Now we need to discuss what are some of the quantities we might want to learn for the HMM. So again, we generate the generative process. Now we get some data, and we have to do the inverse process of learning some of the underlying parameters of this model. So with the HMM, there are 3, it's usually broken down into 3 values of interest that we would want to learn. The first is the state estimation. So in this case, we're assuming that we're actually given the HMM, we're given the initial state pi, the state transition matrix A, and the emission probability matrix B, so we're going to assume discrete HMMs for the rest of the lecture. And we get the observed sequence x1 through xt. So we assume that we always have the data, and we assume we're given an HMM. Now, quantity of interest that we might want to estimate is what is the state that we were in at time I. So we have this sequence in this HMM, and now we ask, at time I in this sequence, which of the S states was I in? So we don't know this because that's assumed latent. We assume that we are not given that bit of information, and so we need to infer it. And so we don't actually find out which state I was in at time I get a distribution on the states that I could have been in at time I. And to do this, we use something called the forward-backward algorithm. And we're not going to be able to discuss this algorithm in much detail in this course. But it's a fundamental algorithm for the HMM, and my goal is to motivate where it's used, and so that it makes it more clear what the purpose of learning this is. So we use the forward-backward algorithm, and out of this algorithm, which takes in the HMM parameters and a sequence, what we can get out of it is the posterior probability, the conditional posterior probability of being in state K at time I, given the entire sequence and given the HMM. So one of the outputs of the forward-backward algorithm is this conditional posterior probability for any time point, for any I and any K. We also might want to estimate the most probable state sequence. So in this case, we're given an HMM and we're given an observed sequence. And now we want to find what is the most probable sequence of states. So here we aren't giving a distribution on the state sequence. We're actually giving a certain sequence of state transitions, S1 through ST, corresponding to the data X1 through XT, where the entire sequence is the most probable one. So we want to find the argmax of the full conditional posterior on the entire sequence, given the entire sequence of data and given the HMM parameters. So it's a point estimate in this case. It's the map solution. And so we actually get a sequence of numbers. This is something that's done through what's called the Viterbi algorithm. This algorithm is a little less fundamental than forward-backward, in my opinion, but also very important and something that we also won't describe in this course. But the Viterbi algorithm is something that is run to give the most probable sequence of state transitions given a sequence of data and given a Markov model, hidden Markov model. Finally, we might want to learn the HMM parameters themselves. So in this case, we're just given a sequence of data, and we are also making an assumption of number of states, S. So we're given a sequence, and we make a number of states equals S. So we make this assumption. And now our goal is to find the parameters of the HMM. And especially, we might want to find the maximum likelihood. So that's the first thing we would want to see if we could calculate. The maximum likelihood parameters of an HMM that are most probable given some data. So this one we'll discuss in a little bit more detail in this course. Let's look at an example of the first two goals that we might want to pursue with an HMM, learning the posterior distribution on which state we're in at a given time, and also learning the most probable state sequence using the Viterbi algorithm. So this is for the dishonest casino. What is shown here is a shaded part and an unshaded part as a function of 300 rolls. So we have a sequence of length 300. During the shaded part, the loaded dice, the unfair dice, is used. So the unfair dice is used for the first 20 or 15 rolls or so. Then we switch in the white part to the fair dice. The gray part is the unfair dice. Then we switch back to the fair dice, and so on. So this is the true underlying state of the model. And now what we observe is not this underlying state, so we don't get to observe the shaded or not shaded, which would be the binary indicator of the state. We get to observe the sequence of rolls, and so that's not shown here, the sequence of numbers of that came up during the roll. However, given that particular sequence of length 300, the forward-backward algorithm can be run, and what we get now is a sequence of conditional posterior probabilities of a given state. So for example, at this time point here, the probability of being in the using the loaded dice, we're saying, is very low. So in this blue line, when it's very low, that's saying the probability of using the unfair dice at that time point is very low. And when this number is very high, for example, in this region, we're saying that at these time points we think the probability that the unfair dice was used is very high. And so these are the marginal conditional posterior probabilities. And so you see that we get very low, for example, in the fair dice period. We say, okay, I believe things are looking fair now. Then we switch to the unfair dice, and suddenly we start moving up and saying, I think the unfair dice is being used here. Then we move down. And so you can see in general, it's able to track which dice is being used, not perfectly, and we're never certain. We only have probabilities in this case. The second problem is trying to find the most probable state sequence. And so this uses the Viterbi algorithm. The most important thing to know right now is that this is not simply a process of rounding this plot. We don't simply take these probabilities and round them to the most probable state and then return that as the most probable state sequence. Because remember, we have a sequential dependence here. So the most probable state sequence takes into account a more global view of the situation. It's not simply a local view. So what this, remember, is plotting is, if I only look at time point 50, what is my belief about which state I'm in? Forget all the other time points. Just tell me right at this time point, what's my conditional posterior probability of where I'm at right now? And so that's what this is plotting as a function of time. Here we're plotting the most probable sequence overall. And so it's more probable to stay in 0, say we're saying the fair dice at this time point, and then switch the loaded here. And so we get something very smooth. If we rounded this left plot, we would get things that jump very chaotically at different points. And those jumps are very low probability events given our transition matrix, which says that we stay at the same state with a high probability. So the low probability of those jumps that we would get rounding here are removed using the Viterbi algorithm, which is taking into account not just trying to explain the data, but trying to explain a likely state sequence, a transition of state sequence between states. And so you see here we give up some accuracy. For some of these we might have said it's more probable, for example, here to say we're using the loaded dice, whereas here, because we're taking a global view into account, we say no, this entire period is using the fair dice. Now this doesn't necessarily look good for this problem, and it's an example perhaps of where doing a map point estimate is not ideal. We might want to use probabilities to express things.